Okie dokie artichoke! 6.3 Centripetal force. Look at this guy. This is crazy. He's like my dad's age. It's crazy. Crazy, man. It's crazy. Alright, anyways. So centripetal force and centripetal motion here. What we're going to get into is an object is center falling. So picture spinning something on a string. If you were to let it go, I don't know, here it would fall straight inwards. The string is kind of supplying a centripetal force inward to hold that ball from flying out. That brings me to another term that is often associated with centripetal force, and that is centrifugal force, which is mostly fake. It's described as having an inertial force, and we know that inertia force, yeah, not so much. Inertia is not going to be a force. It's a property of matter. So in this class, centrifugal force, not a force. I'm not going to talk about it other than what I just did, so don't ask me about it. Now, technically there is, a little bit of gravitational force, external to us, but so minute that it doesn't even play an account. So if there is no centrifugal force, F force, how does this ride work? This is the ride where you go in and then you spin real fast and get stuck to the wall and do all kinds of fun things. Basically, the answer is still inertia, but it's not due to an inertial force. Inertia, an object has a tendency to do what it's doing. Well, this velocity here has it going this way. So if you were to let this go, the string broke, it would fly in that direction. This is what the object is trying to do, right? It's trying to go in this motion. It's trying to go straight. It's trying to do what it was doing, but centripetal force is causing it to turn. So the object would move in a straight line forward, but because of centripetal force, Fc, it's caused to turn. And that's how that ride works, and that's how a little spinning wheel works and all that fun stuff. Centripetal force is like any other force. It's mass times acceleration, only this time it's the acceleration in a circular motion, so AC, centripetal acceleration. And that is equal to the mass times the velocity squared divided by the radius. Key points: centripetal force, center falling, always pointing towards the point of rotation, always pointing towards the center. Acceleration, always going towards the same way as the force. So they're always going to be perpendicular to the velocity. So as this goes around in a counterclockwise way, centripetal force and acceleration always point towards the center. Alright, so let's do a couple practice problems while we're at it. So let's say we have an object that spins around 6 times in 11 seconds. At the end of the rope, it's 2.5 meters long. If the tension in the rope is 70 newtons, then what is the period of the object? Well, going back to the unit before, sorry I'm talking so fast, but limited time and all that. Period is the amount of time per spin. So 1.83 is the period. What is the velocity? 2 pi r divided by the period. So 2 pi, radius 2.5, length of the string, divided by the period, which is 1.83. So if you have an object being held by a string, it's going around in this circle. The length of the string is your radius. It's your center point. It's what you're orbiting around. 8.58 meters per second. So what's the object's centripetal acceleration? Right? So 8.58 squared divided by our radius, 2.5. That should give you 29.45 meters per second squared. Now use this to find the force. Well, centripetal force equals our mass. Oh, that's what we're looking for, I'm sorry. times our acceleration. We know our force is 70. So let me extend the page a little bit so I have a little bit more room. Boop. So 70 newtons equals our mass times 29.45. So 2.38 kilograms. All right, let's do a kind of, Matt Damon, The Martian type situation. So we have this space station. Yay, the space station is going to spin around so that the person on it can feel gravity, which means we want it to feel like it is here on Earth. So acceleration of gravity, 10 meters per second squared. The space station itself has a radius of 150 meters. What would the period of the space station be? We're looking for a capital T. To give it the same acceleration that we have here on Earth. All right, so first things first, our acceleration of gravity is going to be equal to our centripetal acceleration, so 10. Yay. Equals v squared divided by our radius, which is 150. So this will give us our velocity, which is we can then use to figure out 2 pi r our period. So our velocity should be 38.73 meters per second. So 38.73 equals 2 pi r divided by t times t on each side. And that should be 24.3 seconds per spin. All right, sounds good. I will see all of you later. Congratulations. Talk to you later.